Hello, this is Mr. Weideman at Lafayette High School, and this is our AP Physics class. And we're going to be discussing some contents of continuing our discussion of electromagnetism, the relationship between electrical current and magnetism. And we're going to learn something today about that phenomena, but we're going to kind of recap what we know about how we make a magnetic field. And we make a magnetic field or create it or induce it, if you will. All these words are synonymous with if I flow a current through a wire, I'm going to create a magnetic field. And we've studied this, but to do this, some particular things have to fall into place nicely for us. For one thing, we started our study in this charge. It has to move. I'm not going to create a field with just a plain old static charge. I have to make this thing move. It has to change in position. Okay, so if I'm going to move this charge, well, that's a current. And it takes a voltage to do that, to move that charge and get my current. All right, so that's one thing that I have to happen. It's not just a charge, but a moving charge. All right, another thing that has to happen is this field is going to be created perpendicular. All right, these fields are vector quantities, and direction is very important. And we have our right-hand rules that are based on these, the current and the magnetic field being perpendicular to one another. Okay, another critical attribute that we talked about is if I increased the number of coils, I can increase the strength of this magnetic field. And we also learn with our right-hand rule that the direction of this current is also important. But I get all these things coming together, and I am going to induce a magnetic field. And we even had an equation that took all these particular physical attributes together, and we could calculate the strength of a magnetic field created by a coil. And okay, that's pretty amazing. But I'm going to take this equation, I'm going to simplify it a little bit. And number of coils, that's our solenoid. Permittivity of free space, that's a constant. The size of our coils, 2 times the radius, that's all kind of a constant. So basically, as I fluctuate my current, I'm going to fluctuate the strength of the magnetic field. Those two are directly related. And if this goes up, the field is going to go up. If that goes down, then the field is going to go down. So if I fluctuate current, which I can do by fluctuating voltage, I'm going to fluctuate the strength of the magnetic field. All right, well, that's all kind of cool. We know that a current will make a magnetic field. All right, it might not sound amazing at first, but what Michael Faraday discovered in 1831, and your textbooks will say, oh, this is enormously important, and that is an understatement. What Michael Faraday discovered is this little process is reversible. If I change the magnetic field, then I am going to make a current. Just like if I change the current, I'm going to get a change in my magnetic field. And what he discovered is, well, if I do just the opposite, if I change a magnetic field, I'm going to make a current in a coil. And this discovery is basically the foundation of alternating current electrification. And how does that impact mankind? Well, the shorter list is to say how electrification with alternating current has not affected mankind. This is actually extremely, this phenomena that Michael Faraday discovered was really the basis of all of our alternating current electrification. Okay, so this is what's going on. All right, so I start here with a magnet. So we have this magnetic field right here, and nothing is happening. Everything is kind of boring, right? And we know from our study of magnetic field, okay, we see these are like the tips of the arrows, right, stabbing through that loop. Okay, but nothing happens until, just like I needed to make the charge move, I needed a change. Well, to make a magnetic field, I need a change to make a current. So what I'm doing here is I'm shoving the magnet closer. So what does that do is by proximity to the magnet, I've got more field lines going through the loop. So I have made a change in the magnetic field. I made the magnetic field in that loop stronger. And this made a current in the wire. Okay, so we've got some demonstrations set up here for class, and we'll have several workstations, and we'll do this tomorrow in class. And we're going to kind of recreate what we just saw on the last slide. We've got some magnets and some solenoids, some galvanometers and things like that. And we'll be able to see this effect that we saw on the previous slide ourselves tomorrow in class. Okay, now what we're going to talk about here is I needed a change to make a current. Well, there's a lot of different ways to make a change. In this particular slide, what I'm doing is we saw that as I shoved the magnet closer, I induced a current because it made the field inside the loop stronger. Well, I can do the exact same phenomena by making the field weaker, by pulling the magnet away. I get the exact same effect and exact same magnitude. I change that field, I'm going to get a current. But what's interesting is that current, you probably discovered when you were playing with this in the demonstration, is the current is in the opposite direction. And on your galvanometer, yeah, you got that voltage, but the voltage switched polarity. And that is a phenomenon that we're going to get into in a little bit more depth in our next unit that is expounding on Faraday, what he discovered, Russian scientists called Lenz. But this is no accident that this current goes in the opposite direction. Okay, so we discovered that if we change this field, that I'm going to induce a magnetic, I'm going to produce a current. All right, so Michael Faraday, that if I did this, the quicker I made this change, the better it's going to be, the more current I'm going to produce. So not only is changing the magnetic field important, but changing it quickly is also important. So if we're going to do this, we need a way to put some numbers to this. How are we going to quantify this magnetic field going through a number of these loops? All right, and so like just about every other physics concept, we've got a mathematical model. And this is our mathematical model for this phenomena, this number of field lines going through a loop. And it's called magnetic flux. And we call this magnetic flux Webers. And it is, I can multiply the strength of the magnetic field in Teslas, the area of the loop in square meters, and this orientation, just like when we were going to produce a magnetic field with a current, they're perpendicular to one another. These are vector quantities. So it is important that the flux be perpendicular to the area of the loop, or at least have a perpendicular component. And that's why we throw this cosine theta in here. Okay, now to get this orientation, we're going to do something here that's a little bit difficult to understand. Okay, we call it an area vector. And this area vector is going to help us define how perpendicular if you will, the loop is to the magnetic field. And here in this particular orientation, theta is 0, meaning that the way this area is facing, and the way I define how this area is facing, is by a normal to that area. Okay, this arrow right here is normal to the area of the loop, and it is also parallel to this field. So if I change the orientation of this loop to something like that, okay, its area is not facing as perpendicular to the field as it once was before. And this new angle between the normal and the field line is the angle cosine that we put into our equation. And that's how we calculate the maximum value for Webers. That also depends on the orientation of the area. And this will, of course, be maximized when the normal of the area is parallel to the field lines. That's going to give us our maximum amount of flux. And then at 90 degrees, it's going to go 0. Right? There's not going to be any field lines passing through the area. Okay, and this is a little bit difficult concept to grasp. So I've got a little demo that we're going to do tomorrow in class. And we're going to use a hula hoop to look like a coil of wire. And some students are going to hold up some meter sticks that represent the field. And we're going to kind of talk about this cosine theta a little bit more and kind of clarify how cosine theta is used to determine how perpendicular our loop is to the magnetic field. And we're going to pick this discussion up then on the next video. Thank you for your time.